Hey guys, in today's lecture, I want to talk about the statistical mechanics of non-ideal systems. Um, so, stat mech of non-ideal systems. So, this subject, when I say non-ideal, I mean a system where we have certain behaviors of the particles involved that make it um, very difficult to predict what they're going to do. Um, difficult to predict behavior. So the problem with these sorts of systems where the behavior becomes difficult to predict is that we have to approximate thermodynamic quantities. Approximate thermodynamic quantities. We cannot get exact descriptions. Quantities. And it turns out that applying suitable approximation schemes to various systems of these non-ideal systems has become a major component of statistical mechanics today. So what we're going to do is today we're going to consider one such non-ideal system because a lot of modern stat mech is trying to find these approximation methods for thermodynamic quantities of these non-ideal systems. And one common example is a gas of weakly interacting molecules. So this is what we're going to be considering. And when I say weakly interacting, I mean we're considering the low density limit of this gas. It turns out that if you don't consider the low density limit, then more exotic interactions between the particles and quantum behavior starts to matter more when you have a sort of tight density or high density limit of these gases. So for a first approximation, we can consider the weakly interacting system. So it turns out there were earlier models to understand phase transitions in thermodynamic systems. We considered the van der Waals model. So van der Waals model. And just to briefly write down what the model was, we had pressure plus parameter A n squared over V squared times V minus NB equals NKBT. So this was actually a modification of the ideal gas law to sort of account for this. So this was a modification of the ideal gas law to account for molecular interactions, and it turns out that you can see that the ideal gas law components still hold P, V, and then NKBT. However, we added this term and this term, which sort of make it suitable for approximating non-ideal systems, which means interacting systems, non-ideal gases. The reason why we subtract NB is because you cannot compress molecules down all the way to zero. So the smallest you can bring it down to is the volume of the particle itself, or the size of the particle itself. So N times B being the total volume of these particles themselves. And you cannot bring the volume below how big these molecules are together. Um, and when we take into account short range attractive forces, and basically this can, you can think of this as sort of the electromagnetic interaction term. So short range attractive forces can be approximated using this term. And then this is the incompressibility of gases down to zero. And that composed the van der Waals model. So we now try to do, so again, this model only holds true as an approximation. And what we're going to do today is build also another model that's more realistic, but also is really only an approximation. But it is going to sort of start from first principles and build up. So let's get started then. Oh, yeah. So we first consider a one-dimensional, sorry, not one-dimensional, one particle, single particle, um, single particle partition function, single particle, and this is given by Z1, which is just the sort of sum of all the Boltzmann factors of your system. So it has this h cubed factor out front, which is for dimensionality, and it sums over all your position, and this is R, and momentum states. And you have a Boltzmann factor here. So this integration is over all positions and momenta in the phase space, and this is the Boltzmann factor. And this is just how the partition function is defined. So, just a reminder, our partition function is just the sum of all the Boltzmann factors of different energy states. So these are the Boltzmann factors. Boltzmann factors. And so, yeah, this is a discrete sum when you have discrete energy states. But then you can turn this into a continuous, when the spacing between energy levels becomes infinitesimally small, you can turn this into a continuous sum. And the way this, well, the more general formula is really Z1 equals beta times your Hamiltonian is a function of your position and momentum, cubed R d cubed p. And this H is just your total energy in the system, the Hamiltonian, P squared over 2m plus some potential energy. So the region of integration for these for this partition function, right? We're integrating over some spatial region, and that is just some box with volume v. So some box with volume v. This v is different. This is the potential energy. I can use u here. U. This v is the volume region where my gas basically exists, and the partition function sums over all the position states confined within that box, v. And now, if you do the same thing, right, and of course, this is dimensionless, and for you to actually get some uh, dimensionality, we have uh, the Planck's constant over here. Okay, so for n particles, if we want to write down the same wave function for n particles, we have Zn, which is the n particle partition function, equal to 1 over n factorial integral of d cubed r1 d cubed rn. Let me get rid of the van der Waals model. Don't need that anymore. And then you also have these are your positions for n particles, d cubed. So you have 3 spatial coordinates for each particle, and you have n of them. So your integral is with respect to r1 up to rn cubed. And of course, the same thing for momentum. You have momentum in x, y, and z for each particle, and you have n of them. So we have d cubed p1, and then up to d cubed pn. And of course, you have the e to the minus beta times u. And that's just my energy of the energy state, energy of the system, this is the Boltzmann vectors part of the equation. So now the thing is, right, each of these integrals, right, this is one integral for one molecule's partition function. It gets a factor of h cubed up front. So if you have n of them, you get h cubed n times, which is h to the 3n. Okay, and so indistinguishability of particles, so we don't want to double count these partition functions or these states. So since if I have 3 particles in this system, 1, 2, and 3, so 1, 2, and 3, if these are identical particles, right, 1 and 3 being swapped is the same as the original configuration. So if I had 3, 2, and then 1 here, that's the same as having 1, 1, 3, 2 is the same as 3, 1, and 2. So due to this, to account for this sort of internal redundancy, you don't want to overcount in your partition function, so we divide by n factorial, which is the number of ways we can arrange the particles. Okay, so yes. Um, let's also, yeah, and our U is defined, which is the internal energy, is just defined as P1 squared over 2m plus P2 squared over 2m plus, and then you go up to Pn over 2m. And this is just the individual kinetic energies of each of the particles. And you have n of them, so this U is a sum for all. Okay. All right, cool. So I guess I can erase this. Yeah, so we're really going to be dealing with this partition function the entire time. We don't care about the one particle case. So I'm going to erase this. Okay. Okay. Nice. Right. So what I could do here is I can actually write the same partition function for n particles as 3 times capital N integral d cubed p1 d cubed pn d cubed r1 d cubed rn. And the exponential, since the u itself is a sum of all of them, of the kinetic energies of each particle, there's a sum in this exponent, so I can split it up into these products over here, like p1 squared over 2m e times negative beta p2 squared over 2m, and so on. So since I have this product here, I can actually rewrite that in just a second. But before that, I want to say that these momentum integrals, so you have 3 momentum integrals and 3 position integrals for each of the particles. So we have 3 position integrals, 3 momentum integrals for each particle. So 1 particle. And we have n particles, so we have 6n integrals. Total integrals. So it's kind of crazy to think about, because n is like on the order of 10 to the 23, and we have 6 times 10 to the 23 ish integrals that we're dealing with. So clearly we can't sit here and evaluate 10 to the 23 integrals. So we want to sort of find some clever ways where we can simplify this partition function. And once we simplify this partition function, in some way, which is what's going to take the most amount of work, then we can start using statistical mechanics to take derivatives of the partition function and find Helmholtz free energy, pressure, and all that. So that's sort of the plan now. So how do we evaluate this position integral? I mean the momentum integral. It turns out that these exponential factors out front only depend on momentum, not on position. So we can sort of group that back in over here and just integrate it that way. And it turns out that if you do this for an ideal gas, we get something like Zn. So what I'm saying is if we integrate just the momentum parts, including the exponential, because it depends on momentum, for an ideal gas, what we got is Zn. Hang on, let me write it like this. So the integral over momenta pi for pi squared over 2m equals this 2 pi m kbt cubed. And this is for an ideal gas, and the reason the way we get this is I can do a quick derivation for this over here. So for one particle, we have the integral of e to the minus beta p squared over 2m equals, and of course we're going to do this for px, py, and pz. So this is e to the minus px squared over 2m dx, right? Or dp, sorry. Dpx px integral negative infinity to infinity 2m and times pz squared over 2m. Oh, this is dp y dpx dpz, sorry. We do this, right? And it turns out that each of these integrals is just the Gaussian integral. So these are just 1D Gaussian, and each of those evaluate to square root of pi over a cubed, where this is the integral of e to the minus a r ax squared dx. So this is just the 1D Gaussian, so I just have to evaluate each of these using that same idea. And it turns out that if I use the same formula for this, each of those integrals, each of those momentum integrals, multiplied together when I evaluate them, to the minus, this is this, pi squared over 2m is just 2 pi m over beta to 3 over 2. And since beta is just 1 over kBt, 2 pi over, and then 1 over, this is 1 over beta. Beta is 1 over kBt, so I get kBt over here. And that's what I get, which is the same as what I had over here. So that's basically how you evaluate the momentum part. You just you split it up into px, py, pz, invoke the Gaussian integral, which is just that, and then you just multiply them together and you get this. And that's what I have here. So, of course, that's just for one particle, and you have, so if this gives you, if this is for one particle, and I get this this factor once, essentially, I'm going to get it n times when I do it for n particles. So that's the idea there. So instead of having a 3 here, I'm going to have 3n. This is what's going to happen. Right. So, like I said, I'm going to have n of them. So this total partition function for n particles, when I evaluate the momentum part now, I just get Zn equals 1 over n factorial, 1 over h to the 3n. These factors stay. And then the same as what I got earlier, the 2 pi m kBt to the power of 3n. It was just 3 before for one particle, but then for n particles, 3 to the n, to the power of 3n. Okay, nice. And of course, this is just the momentum part evaluated, and I still have the position part, which is left. And that would be the rest of this equation. So d cubed r1 cubed rn times e to the minus beta u potential. And the reason why I still have this e to the u potential is because this u is total energy, but then when I do the kinetic energy part, I get p squared over 2m for n of them, and that's the p-dependent part of this Boltzmann factor. But then I still have potential energy, which depends only on the distance between the particles, which is r. So I still have the potential energy part of that integral left. So that's why I still have this. And this integral right here, I'm going to rewrite it over here. So this is my total partition function right here after evaluating the momentum parts. And now we have this integral over here. E to the minus beta. This part right here is known as the configuration integral. So this is the configuration integral. Configuration integral. And the reason is, right, it integrates over all configurations in space of the particles. Therefore, we call it the configuration integral. Nice. Okay, so now we actually get into the, so I guess we're sort of done with the preliminary setup of the problem. And the idea is to sort of evaluate this integral now, or, try to sort of break that integral apart in some clever way. And the rest of the thing that we're going to do involves that. Okay, so I'm going to get rid of this. Yeah, I think I'm going to get rid of this too because we have it boxed over here. All right, nice. So again, I can just, so if you notice, U potential is just going to be the potential energy for sort of like pairs of particles. So if I write this, so now what we're going to do is known as the cluster expansion. The cluster expansion. So the cluster expansion. So if you'll notice, U potential is just the pairwise sum, 1, 2 plus U 1, 3 plus U 1, 4, right? Up to, plus U 1, N plus U2, 3. This keeps going up to U n minus 1 and U n. And this is equal to the sum of Uij. I'm just showing you what the potential energy looks like. And this is the pairwise interaction of molecule I with molecule J. So that's the potential energy between I and J. So we have this pairwise sum of all the interactions between particles. And we also say that this this interaction only depends on sort of the distance between the particles. So, depends on, it's only on distance. So it's going to be dependent on the quantity J minus Ri. So that's the distance. And so now if I take this into account, writing out the potential energy, you see how it looks. I can rewrite my configuration integral as a product. So over v to the power of n. Okay, so the reason why I have this, let's see. I think I forgot to mention something earlier. Oh, so I actually forgot to mention one thing. There should be a factor of v to the power of n here. And the reason is this over here, we can think of this as just z ideal times 1 over v to the power of n. This is because this entire thing right here is really just the, this part over here is really just the partition function for an ideal gas times 1 over v to the power of n. That's because this times v to the power of n gives you the partition function for an ideal gas. So really, what we're looking at is z ideal times 1 over v to the n, and that 1 over v to the n times this position integral part is the configuration integral. So which is why we get this 1 over v to the n over here. And I said that we're just going to rewrite this in terms of this pairwise sum, which turns into a product, as you'll see. It's really just r1 d cubed rn, and then I have the product, pairwise product, because exponential with a sum in the exponent just splits up into products. Okay, so this is the way we're gonna write it down. And we also say that we're looking at the low density limit. So low density limit. So we say that uij is much, much less than kBt. And the reason, if it's a low density limit, the distance between molecules is large enough for this potential energy term to be much smaller than kBt, the temperature scale. And since this is true, we know therefore that e to the minus beta uij is approximately 1. Awesome. So that's what we're going to do, and this is only due to the low density limit. All right, so now I guess I think I'll get rid of this over here and just rewrite it. Yeah. Nice. All right, so it turns out that any deviation of, so this is what we would expect it to be, right? A 1 in this low density limit. But of course, you could argue that what if there are some particles that end up being close enough to each other where the interaction is actually not negligible, and this is actually large enough for it to matter. So we can think of it that this is the ideal low density case. However, it doesn't have to be exactly that. So it could be some deviation from that ideal low density limit. And this is where we, so deviation from low density limit, density assumption, I should say, is given by e to the minus beta uij equals 1 plus some deviation, which is this. And we call this deviation the Mayer F function. All right. So the product of all these Boltzmann factors now is just, so this product of is just pairs 1 plus Fij. And you can think of this as 1 plus F12 times 1 plus f13 up to 1 plus f1n times 1 plus f23 1 plus f n minus 1 comma n comma n, like that. So this is the Mayer f function, and if they're all multiplied together, notice how the first term would just be 1. So 1 times 1 times 1 a bunch of times is just 1. But then the next term will involve the product of f12 times all the 1 terms. So you would get a term with just f12 in it. And then you will do the same thing for f13. So you will get another term with just f13 in it. And then if you start multiplying f12 with f13 and the other f functions, then you get terms with f12 times f13 times f14 and so on. So essentially the pattern that you'll see is we get, so the product, pairwise product, you'll just get 1 as your first term, which is just the product of 1 times 1 times 1. And you will get a term, a bunch of terms, with just f sub ij in it, because that's just the products where you take these f functions from each of the terms and multiply by the ones in every other term. And that gives you this sum over here. And again, pairs. And then that plus the next term in this product will be f12 times f13 times a bunch of other f functions. So you would get fij, fkl, I guess, in distinct pairs. So you can think of it like this. And this is kind of crucial, you'll see. So now what happens is the configuration integral can be rewritten as, let's see, can be, can be rewritten as, what we had before, cubed Rn times 1 plus this Fij plus sum of Fij Fkl, like that, and so on. So this is what we have so far. And one more thing you should notice is that this integral just gets multiplied by this one term, by this sum term, by this sum with the 2 Mayer f functions term, and then 3 f functions, I should say. This is really something that continues, right? So you're going to have this integral getting distributed amongst all these terms in the sum, which come from the product. So we're going to have to deal with that, and I'll show you how that works. So maybe I can write this in the corner here. Integral Rn times your product of e to the minus beta Okay, like that. All right. So yeah, so this integral where it gets multiplied by the one. Think of it as integrating um, over d cubed r1, d cubed r2 up to rn. So what that gives you is you actually get a factor of like the volume of the box itself to the power of n times this 1 over v to the n. So you get so the first integral, first term in ZC equals just 1. And the reason is 1 over v to the n times d cubed r1 rn equals just 1. This makes perfect sense. So then now we're stuck with, now we look at all the terms with, so we took care of the one term. So now we have to look at all the integrals when the integral gets multiplied by this 1 Meyer f function term. How are we going to deal with that? So we get 1 over Vn integral d cubed r1 d cubed rn f12. I'm just considering one of these integrals because, of course, this fij itself is a sum, so that's going to split up. But if you just look at the first term in that 1 Meyer f function term, you get f12. And really, if all we need to do is evaluate this, and then we just know that we're going to get the same thing like n times based on this pair that keeps switching. So we're going to get v to the n times, right, oh yeah, we get d cubed r1 d cubed r2, and then we're going to get a v to the power of n minus 2 here. And let me tell you why. It is because this Meyer f function only depends on the distance between molecule 1 and 2. So really, this f12 depends on r1, r cubed 1, and r cubed d r cubed 1 and d r cubed 2. So every other d integral disappears to just the volume of the box, and only the term which depends on the Meyer f function itself survives, which is what this is. And of course, you have your, I forgot to write, f12 Vn minus 2. So basically, only the particles' positions r1 and r2 matter for this Meyer f function. So v to the n minus 2 comes from the fact that if you have n particles in your system and two of the integrals actually do not disappear due to this pairwise interaction here, n minus 2 integrals turn into just v, so you have v to the power of n minus 2. Right. Yeah. So this only depends on R1 and R2. Nice. And it turns out that since we don't, it doesn't matter which one we call molecule 1 and which one we call molecule 2, every single one with the one Meyer f function. So I told you this is only the integral for f12, but then if you do the same thing with d cubed r2 maybe this time, and d cubed r3 maybe this time, and then you have f23, this is going to give you the same thing because you're going to get basically the same thing. And since these are just arbitrary labels, which is 1 and 2, so for all I know, 2 and 3 could be the same as 1 and 2. So they all basically just give you this same factor over and over and over again, because it doesn't matter which one I call 1 and 2. So your one Mayer f function term in the configuration integral, which is this, is literally just this times basically the number of distinct pairs out of the n particles that I can choose. So this just gets multiplied by, so we get 1 over v squared integral d cubed r1 d cubed r2 f12 times the number of distinct pairs of n molecules, which is n choose 2, right? So you get that same factor, n choose 2 number of times, and n choose 2 is precisely the number of terms in this sum right here, which makes sense, right? So this integral just simplifies to 1 over v squared integral, let me rewrite it like a slightly better way, of n factorial all over n minus 2 factorial times 2 factorial, just the permutation formula, times 1 over v to the power of v squared, right, times the integral d cubed r1 d cubed r2 f12. And if you do some simplifying here, yeah, so you can rewrite this as n times n minus 1 times n minus 2 factorial all over n minus 2 factorial times 2 factorial d cubed r1 d cubed r2 f12. So now this cancels with that, and I just get n times n minus 1 all over 2v squared integral d cubed r1 d cubed r2 f12, like that. So I think you can see that. Right. Just want to move this back a little bit so you can see that. Right. I think you can see it. Yeah. So this is the first term in my Mayer f function. The second term in the configuration integral, which is this. Nice. So I guess what I'm going to do is I'm going to write this down so it becomes explicitly clear somewhere. Let's see, maybe over here. I'm going to write it up here. So your z sub c is basically just d cubed r1 d cubed rn times your 1 plus the sum of fij plus the sum of ij fkl, like that. Nice. So this is something good to have in front of you. And basically what we determined is that is just 1. So this is the first term in this integral. So, and then z sub c comma 2 is when we take that entire thing multiplied by the 1 Mayer f function, we get that over there, which is n times n minus 1 over 2v squared. N times n minus 1 all over 2v squared, integral of d cubed r1, d cubed r2, d cubed r1, r2, f1, 2. And now we want to sort of get like a, we want to keep going, right? We can't just stop at the first term. So for convenience, what I'm going to do is I'm going to define this so basically this is the integral that talks about all the interaction between two particles, f1 and 2. So this is the integral that controls interactions between pairs of particles. And I'm going to define this with a diagram, which is just this line with 2 dots. So that line with 2 dots just basically represents 2 molecules, and the interaction is the line, which represents. So now the idea is we want to try and translate this entire configuration integral into basically a bunch of these sort of pictorial looking graph or whatever diagrams that you want to see. So the next thing that we want to do is consider of course, naturally we did this term and this term. We also want to look at with the 2 Mayer f function terms of the configuration integral. So again, we're trying to do zc comma 3. And this, we're examining. I'm going to get rid of all this now, because essentially what we need is up there. So we don't really need this. Yeah, now we're getting to something a little interesting. It's going to be fun. I can't find the chalk. There we go. So now look at 2 Mayer f function term. And we're looking at the integral d cubed r1, d cubed rn, fij, fjk, I'm going to call it. Yeah, maybe I should call it the same thing both places. So that's jk. So j and k. Nice. So if we want to do this for consider, so I'm going to say consider f1,2 and f2,3. So if we do this for f1,2 and 2,3, so this is remember what the Mayer f function is. It is the deviation of this particle from the low density limit. That's what f functions represent. So this is the interaction between particle 1 and 2, and this is the interaction between particle 2 and 3, and that's the product of them both. So now what we're looking at is if we basically write down this integral just for f(1,2) and f(2,3), so I'm picking one specific term in this sum, which is 1, 2, and 2, 3. I get 1 over v to the n integral. Remember what happened with the two-particle case. Every integral except for the ones that the Mayer function depended on canceled out, or not canceled out, evaluated to v. So only the d cubed r1 and r2 stood for the f(1,2) Mayer f function. So over here, since we're looking at f(1,2) and f(2,3), we expect naturally that this would remain. We also expect this to remain, and the 3 to also remain, r3. And, of course, the Mayer f function itself, f(2,3). All right. So now notice that in this sort of orientation of the Mayer f functions that I'm considering, f(1,2) and f(2,3), so the particle number 2 is being shared between 1 and 3. So you can think of this as sort of like a common interaction. So there's an interaction between 1 and 2 and 2 and 3. So both particles 1 and 3 are interacting with 2, essentially. That's what's happening here. And now we want to figure out, and since we have n particles, and we're only involving 3 of them in this integral that we're considering, n minus 3 v to the n factors is what we get. So really this is, so this integral, when we put it in terms of 1, 2, and 3, it turns into this. Same reason as how we did it for the other one. So this gives you 1 over v cubed. Sorry, 1 over v cubed times the integral d cubed r1, r2, r3, f(1,2), f(2,3), like that. Yeah. All right, nice. But the problem is, right, there's something peculiar that happens here. This is only one such sort of combination. So if you think of what I'm trying to represent, diagrammatically, it looks something like this. So it is sort of an interaction. So if you consider this particle number 2, so it's the particle that's shared, this is 1 and 3. Notice how we have this interaction between 1 and 2, interaction between 2 and 3. And the 2 is the common molecule in this interaction. Say over here it was 1 and 2. But notice how over here I can actually just swap these two. So I can, if this is 1 and this is 2, that is basically the same as saying 2 over here and then 1 over here, because these are indistinguishable particles, right? So 1 over here. So it's basically the same thing where you can swap them and the diagram remains unchanged. Over here, I have 1, 2, 3 like this, but I can also very easily just do, of course, 2 stays the same because I can't change the location of 2 because those that is the shared particle between the two. So I can change this to 3 and this to 1, which is also the same exact thing. So I want to sort of account for this sort of swapping. Notice how I can change. So this is known as the symmetry factor. And the way we're going to actually draw these diagrams for these integrals is we now think about it, right? For f(1,2), I didn't have to choose particle 1 and particle 2. I could have done particle 2 and 5, 3 and 7. So I could have chosen any pair essentially. And that's why we had this n choose 2 factor that came in front, and then my integral simplified to this. So you can think of this as, let's say I'm considering a two particle interaction. So two particle interaction, particle interaction. So I have two slots essentially. I can choose some particle to be the first particle in my interaction, and then some other particle to be the second particle in my interaction. So I have n choices for the first particle, and I have n minus 2 choices, n minus 1 choices for the second one. So I multiply these two, and those are sort of like the number of combinations I have of two particles. You know, if I have two particles, two slots, the number of combinations is just this. And that's why you see this sort of n times n minus 1 factor that shows up in front of the two particle interacting integral. And this 2 over here at the bottom, this 1 over 2 factor, really is called the symmetry factor, and it comes from the fact that not only do I have n times n minus 1 different ways this integral can be represented, but I also have a degeneracy, so I can swap 1 to 2 and 2 to 1, and that's basically the same thing. So half of these, so this introduces a symmetry factor of 2. So I divide out by that symmetry factor to avoid overcounting, essentially. And if you think about this for the three particle system, really what I'm doing in this case is a three particle interaction, right? I have n choices for my first one, and I have n minus 1 choices for the second particle, and n minus 2 for the third particle. So, you just multiply these factors out, and that is sort of the factor of the number of ways I can arrange that I expect to show up over here. And which is exactly what happens when you evaluate this integral. I'll write it down in a second. But let me ask you, think about what would the symmetry factor for this be? The symmetry factor would also be really just 2, right? Because I can swap 1 to 3 and 3 to 1, and that would be a factor of 2. So I would have to divide out this integral by 2 eventually. So 3 particle, I get this divided by 2. And remember, all these integrals end up getting this volume factor. And remember, if I have a v to the power of n constantly in all these integrals in the front, but then when I actually evaluate, if I'm doing an interaction of 3 particles, n minus 3 integrals turn into v. So I would get like a v to the power of n minus 3 over v to the n, which is a v to the 1 over v cubed. And same thing over here, 2 particles involved, so I get like a v to the power of n minus 2 on top, divided by v to the power of n, so I get a v squared at the bottom. So I also expect there to be a v cubed here, of course. And my integral, which is just this part over here, r1 cubed, r2 cubed, r3, f(1,2), f(2,3), like that. And this is a shared interaction. And what I'm going to do is I can just represent this integral by that dot thing that I showed you guys earlier, which is just this. Yeah. So that's what we're doing there. So I guess I can add this to my arsenal now, where I can say that I have n times n minus 1 times n minus 2 all over 2v cubed times the integral d cubed r1 d cubed r2 f12. Oh, I forgot. d cubed r3 f12 f23. All right, just like that. And I am going to define, let me get rid of this. I can define this integral as this 3-dot diagram. It's really simple if you think about it. Quite simple, a concept. I get this. So that's sort of the library, so you can keep referring to that as we go on. Nice. Now, we also want to, think about we did like this 3-particle system, but then notice how the particle number 2 was shared between 1 and 3. We also want to consider the 2-Mayer F function case where it's not J here, but we have no particles shared, but we have 2 pairs essentially. That's what we're going to do now. I'll show you how that works out. All right, so we want to consider L, let's say. So basically, now every single particle is unique. In this case, my diagram looks something like I have an interaction between I and J. So I and J, some interaction. I also have some interaction between L and K, like that. So that's the interaction I'm looking at now. And you want to really think about it the same way that we did the other integrals. If we're doing something like, if we have 1, 2, 3, 4, let's say over here, we're going to have, remember, it is now 4 integrals that remain, and every other integral gives you a factor of v. So I would get v to the power of n minus 4 on top, and then v to the power of n here, times, and then I would get, remember, I can choose the particles that are involved in this sort of 2-pair distinct interaction. I don't have to do, I can do n choices for the first particle, n minus 1, n minus 2 times n minus 3. So I would get essentially n times n minus 1 times n minus 2 times n minus 3 choices there, all over the symmetry factor. Now this one can be tricky. How many ways can I rearrange I, J, and Lk without changing the way the system looks? So I can swap I and J, so that gives me a factor of 2. I can swap K and L, that gives me another factor of 2, so 2 times 2. And then I can also just do LK over here and IJ over here, which is another factor of 2. So that's a symmetry factor of 8. So I divide by 8 here. And of course I get my integral that's left, which is d cubed r1, r2, cubed r3, r4, f1, 2, f3, 4. Just like that. Yeah, so this is what we get. Going back to my sort of key over here, I can say that z 3 non-shared, let's say, non-shared is, by the way, these subscripts I have here are the terms, the term numbers. So this is the third term. This is the second term. This is the first term. The third term involves both the non-shared case and the shared case, which is why we get n times n minus 1 times n minus 2 times n minus 3 all over v to the power of 4, right, times 8. So I guess I'll say 8v to the 4th integral of cubed r1 d cubed r2 r3 d cubed r4 f1 2 f3 4, like that. And this is defined as this diagram over here. Nice. So now we can actually think of, further terms. I don't want to waste time. So that was the first 2 terms of the Mayer F function. I can write it like this. But I think it's easy to imagine that this z sub c is just going to be sort of this 1 plus this plus this plus this. It's going to be a sum of each of these integrals with different numbers of pairs interacting. And you can imagine that when you sum up all these diagrams for different numbers of particles and different pairwise interactions and whatnot, you would get some formula for the in terms of these diagrams for your configuration integral. And that's what I'll write down now. So these were the diagrams we just derived were essentially just the first 2 terms of the Mayer F of the configuration integral. So if we keep going, right, and we ideally did this for all of them, we would get some z sub c as just 1, which is the first term, plus this interaction plus the triangle term where you have a shared interaction that plus you have this interaction where you have 2 pairs but none of them share a particle. I think this should be making sense. Plus, you have this other triangle term where, you have not only a shared particle, but you also have the other 2 particles interacting as well. So this is another combination. And then we have some patterns that look like this, So, I mean, I think you can see we have to try and do every possible type of interaction. So that's another one where you have a common particle for three different particles, which is quite interesting. And remember, each of these is some integral. And then you can keep going, and you can have something that looks like this. Really, anything that your imagination can think of. But really, you have to respect this sum over here. This sum sort of just keeps going, right? You're gonna have some interaction with all the particles in one of these diagrams. So you have some that are like disconnected like this. So these are like the connected diagrams, these ones. You have disconnected ones that are like this or like this, and this one maybe like that. Running out of chalk here with this. And then you can keep going. It's the last one I'll draw, which is like this type of interaction. I might just edit this part out, actually. Drawing this wastes time. Yeah, something like that. So this idea where you can write the configuration integral as this sum of diagrams is known as the diagrammatic perturbation series. So this is known as the diagrammatic perturbation series. I think there's something very crucial I should mention here. Think back to what these diagrams actually represent. These diagrams would not exist if we did not have a Mayer F function. The Mayer F function is really this deviation from the ideal non-interacting low-density case. So it's a deviation from this non-ideal, from this ideal case, and if a Mayer F function doesn't exist, that means there really is no interaction between those two particles or those three particles or whatever. So really, you can think of all these diagrams as just going off to zero if there is no F function, which means there is no deviation from the ideal limit. So for an ideal gas, really, your ZC is just 1. And 1 is just this part of the integral, which is exactly what we get for the configuration integral of a ideal gas. So you can think of these diagrams as sort of perturbations that you're adding from the ideal case deviating into a non-ideal case, where each of these adds like another interaction to your system. So again, in an ideal system, there would be none of these diagrams. They all would just cancel because all these products of these F functions would just be zero. But depending on how your system is interacting, you can keep adding more and more terms to this series. So I guess like a good approximation where you only have a few pairwise interactions, maybe you can do this much. Or maybe if you have more complex interactions, you can do 3 terms or 4 terms, whatever. So this one term would be like the perfect ideal gas, and everything else is a perturbation from this ideal state, which is why we call it the diagrammatic perturbation series. Since n is large, right, even with a low density limit, we can sort of conclude that the first couple terms are not enough, because even the simplest 2-dot diagrams, like this one, evaluate to a number much, much larger than 1. Like even if you do this integral over here with just 2 particles, since n is large, you're going to have a big number for this term as well. So maybe there is like some way to sort of simplify this or wrap our minds around. And what we could do is we could think of the subseries. So consider subseries of just these sort of disconnected diagrams of this plus this. So we're trying to sort of minimize as many terms as we can in this series so that it's easier to deal with. And maybe there's something interesting that happens when we just consider these disconnected diagrams, like this one. This one I can circle them in yellow, like this one, like this one, this one. Maybe there's something interesting that happens when we consider this subseries of just these disconnected diagrams. So if we do that, we get 1 plus this it's a workout, and so on. Just gotta check if the video's still recording. Yeah. Okay. Yeah. So we have this subseries that we can consider, and even this doesn't converge until many terms because n is large. But we can actually simplify this by just saying, n equals n minus 1, which equals n minus 2, and do some crazy stuff like that. But I think what you'll notice is that each of these terms with the disconnected diagrams, if you look back at the integral, like over here, right, um, let's see, 1, 2, 3. I think I forgot to say something again. So what I want to say is, right, notice how each of these disconnected diagrams, they actually get a symmetry factor of n factorial. By symmetry factor, what I mean is, right, you can swap this diagram over here and this diagram over here. So that's a factor of 2. N is the number of individual identical looking subdiagrams in each of these disconnected diagram terms. So in this disconnected diagram term, I have 2 of these identical looking diagrams, right? And I can swap them and I get a degeneracy of 2. So I have 2 ways of arranging them without changing them. So this gets a symmetry factor of 2 factorial. This gets a symmetry factor of 3 factorial because there's 3 factorial ways of arranging these sub-diagrams. So really, all of these things are just you can think of them as taking this one stick diagram and having it as a power series with the degeneracy factor built into it. And that is exactly because this is just this squared. this cubed equals this diagram, and so on and so forth. Except you have to build that degeneracy into it. So we can rewrite this as just 1 plus this plus 1/2. So remember, this gets a degeneracy factor of 0 factorial. This is 1 factorial. This is 2 factorial. So I get something like this, like that. And then this gets a 3 factorial. By this I mean this term over here. 3 factorial, and it's just this cubed. And this series just continues on. Ah, look at that. This looks very, very similar. So again, I have 1 over n factorial, and I have to the power of n here. So this looks very similar to my e to the x. So I can think of this as an exponential itself of this two-particle interacting integral. It's a bit of a silly idea, but yeah, this is something I can do. It turns out that if we want an even better approximation, so what we've ideally done here is we've written this exponential power series thing, Taylor series, in terms of this two-particle interaction. So essentially, I'm just saying this sub-series that I'm considering can be just a power series of this simplest diagram. So it's an exponential of that simple diagram, which is interesting because then wouldn't it be nice if every other diagram, so I was able to represent this sub-series in terms of this simplest diagram, in terms of an exponential like this, but maybe there's some way of representing all these complex connected diagrams in terms of this simplest diagram. That would be like very nice. And it turns out that if we want an even better approximation, we start to include these terms as well in our series. Again, I only considered this sub-series because as a first approximation, I only wanted to consider those interactions. But then if I try to look at even better approximation, I would have to include more interactions, which means including this, and many more complicated diagrams. However, if there is some way of representing those complex diagrams, just like I did with the sub-series, as an exponential of the simplest diagram, that would be a win. So let's see if this is possible. And it turns, I will just say, yes, it is possible. It turns out that not miraculously, just mathematically, examining this closer, it turns out that you actually are able to represent even more complicated diagrams in terms of this simplest two-particle interaction integral, which is mind-blowing, really. So it turns out that this sub-series actually includes not only what you see, but it also includes these sorts of complicated diagrams. And the proof for that is, you can say 1/2. So just look at the quadratic term in this sub-series, which is this one. And it turns out that this squared is just, it's defined by this integral, 1/2 n times n minus 1 all over v squared integral d cubed r1 d cubed R2 F12 squared. And I'm just going to give you the answer. This one actually simplifies to 1/8 times n to the fourth. This is, again, if you actually evaluate this, you get 1/8 times n to the fourth, 1/4 n cubed, plus 1/8 n squared times this small v squared over this big V squared. This is the volume, and this v, the small v, is just defined as this integral part over here. R1, yeah, so I'll just say d cubed r times f of r, because this is just some function of r, which is, yeah, this squared, v squared. So again, I do this similar thing for my this diagram over here, this one. And it turns out that, again, if I redefine the integral and all that, and I actually write it, I get something like n to the fourth minus 3/4 n cubed 11/8 n squared minus 3/4 n times v squared over big V squared. I get this. And similarly, I'll just do it over here. Now, if you do it for this guy, this three triangle looking interaction, you actually get 1/2 n cubed minus 3/2 n squared plus n v squared over v squared, like that. And if I consider the interaction where I take this diagram, this two-stick diagram, and I add it to the triangle interaction, so I'm basically adding this and this. And when I do that, I actually get the same thing. Again, I'm skipping steps here, but it turns out that when I add this two-stick, which is represented by this expression here, plus the triangle, which is this expression here, and I add them, I actually just end up getting this one-stick expression, which is incredible, because all I'm saying is 1/2 times this one-stick squared is equal to these two diagrams added. Would you look at that? The squared term in this subseries over here ends up capturing the interaction where I have this triangle. So I have now successfully represented this connected diagram also as just this simple diagram. And it turns out that if you keep doing this, even many more complicated diagrams like this one, infinitely complicated ones, not infinite, but very, very complicated diagrams also can be represented as a function of this single simplest subdiagram. And this is a remarkable result here, because then I can just say that z sub c is really just an exponential, just like this subseries of these. So it turns out that it's not only of an exponential of this, which captures many of these diagrams, but also an exponential of this one and this one. And this is not a trivial proof. This is something very, very complicated and not easy to prove in a video. But yeah, something like this. Yeah. Turns out that you can actually add this, and that's what my configuration integral becomes. And this is known as sum of clusters. Clusters. This is why it's known as the cluster expansion. Now, I just have a couple more things to talk about, and then we should be basically done. Don't want to erase my. Yeah, maybe I can erase this over here. Oh. Just a couple more things to talk about. I can now that I have this sort of exponential way of representing my cluster function. If you'll remember from earlier, the total partition function is really just the z ideal, right, times the cluster. The configuration integral. I keep saying cluster. Configuration integral times the ideal gas partition function gives me my total partition function of this entire system. And I can just say the Helmholtz free energy of, this is a StatMech formula, is related like this, which is just negative kB T ln Z ideal times, minus kBT ln ZC. Now we know that this is evaluated in StatMech. This is from ideal gas StatMech. We know that this just evaluates to minus N kBT ln V over N VQ. VQ is the quantum volume. Quantum volume is just, essentially, it's just your thermal de Broglie wavelength squared. kBT times, and I just plugged in, kBT, ln of your partition would just be, ln of your configuration integral would just be these diagrams added. So you just have those diagrams being added. Yeah. So on and so forth. Yeah. And you can similarly calculate pressure. Pressure is just your derivative of your Helmholtz free energy with respect to V, volume, and with N and T held constant, which just gives me N kBT all over V plus kBT partial V of, again, your diagram series. Yeah, like that. We can't just stop here because the problem is, what on earth? Like, we can't just leave it like this. We want to somehow try and evaluate this integral for this single stick model at least. And let's try and do that quickly. It's not easy, let me tell you, to do these integrals. Okay. So what we're gonna do is, right, the second variable coefficient is what we want to derive now. Coefficient. So the second variable coefficient, consider equals 1/2 n squared over v squared integral d cubed r1 d cubed r2 f12. Since this f function only depends on the distance between your two particles, 1 and 2, you can basically say that you can define this r vector, which is the distance between these two vector between r1 and r2. So r2 minus r1, like that. And if we change the variables here into r terms, I can change of variables this integral. When I do that, and of course, f of r, remember from the very beginning how I defined the Mayer f function, it is that deviation of your Boltzmann factor, something we didn't touch on for a while, but it's the deviation from 1. That's what this was defined by. And, if we rewrite this, we can say that this integral just turns into n squared over v squared integral d cubed r1 times the integral d cubed r times f of r, like that. Now I can actually evaluate this integral quite easily because integral of d cubed r1 is just v cubed. So I get a factor of v out front. So this is just v, which is I get a 1 over v. This integral is not easy to evaluate. However, I could say one thing. Think of this as I have some particle pinned at r1, and then this integral integrates over all the other distances possible. So you can imagine, since r is just the distance between r2 and r1, if I'm integrating over r, I'm integrating over all the possible distances my second particle can be from the first particle. So think of this as imagine this is my origin. I have some r1 vector here, and I have my particle 2 somewhere here. This is some r2, let's say. This difference is just r2 minus r1. And what I'm doing here is this is defined as r, and I'm integrating over all the possible distances that this vector can be. That's what this is. So what does that mean? That means this vector, if it's large enough to contribute to this integral, then this integral actually survives. If not, it disappears. Not only that, but this vector is also confined within the volume of the box itself. Since it's confined within the volume of the box itself, I can really reduce the region over which this integral is defined to just the volume of the box. And not only that, if it's far away from particle 1 within the volume of the box, also this integral just goes to 0. So you can think of it as this integral basically goes to 0 in most places, except for when this vector is very small, meaning these two particles are very close to each other, which makes perfect sense again. Nice. And from that, I can just, I can just write this integral as 1/2 n squared over v, because this gives a factor of v, times the integral d cubed r f of r, like that. And I can plug this into the pressure equation over here. Where is it? Over here. And when I plug in, I'm going to erase some stuff over here. Yeah. We're almost done here with this topic. So if I plug that integral that I just got for the simplistic diagram into the pressure equation, I get P equals nkb T all over V times 1 minus 1/2 n over V integral d cubed r f of r, like that. And of course this continues with more diagrams. Yeah. So your pressure can be written as a sum of virial coefficients, as they call it, which is just nkbt over v, 1 plus b of t. Let me remove this equation as well. So it can be written as a sum of your virial coefficients, which are b of t, c of t, over plus some continuous, where I define b of t is defined as 1/2 integral cubed r times f of r. So we just define the virial coefficients as these integrals that depend on the Mayer f function. If you keep doing that, and a lot of times these virial coefficients, look, we already have a decent enough expression for pressure. It's just in terms of these B, C. We already know V, N, and all this stuff. So if we can measure these in the laboratory, then we can get our answer for these thermodynamic quantities. So the second virial coefficient is known as B of t. B of t, how do we evaluate B of t in spherical coordinates? So B of t equals triple integral 0 to 2 pi, 0 to pi over 2, 0 to infinity of f of r, r squared. The reason is it's a spherical box that I'm in, that I'm using spherical. Oh, I forgot the sine theta. dr sine theta d theta d phi. Right. And then these angular parts just turn into negative 2 pi. And I have the other part still stuck, like that, dr. And it turns out that I can't really go any further. If I plug in f of r, I get minus 2 pi integral from 0 to infinity of r squared times e to the minus beta u of r minus 1 dr. So I can't really go further than this without an actual equation for u of r. And that's really like the potential energy interaction function between particles. So I can't really go further without that. It turns out that you need something that takes into account these um, pairwise attractive interaction, repulsive interaction, all combined. There must be some model that's experimentally determined, and it turns out this is known as, like, one common choice that takes into account is known as the Leonard-Jones potential. I'm gonna write that down somewhere here. Yeah. So B of t equals 1/2, right? Yeah. Oh, sorry. Equals 2 pi integral from 0 to infinity of r squared times e to the minus beta u of r minus 1 dr. We need some function for u. If not, we can't really evaluate this. We can do everything else. So a common choice is Leonard. I forget how to spell it. Leonard-Jones potential. This is a potential that takes into account the attractive and repulsive forces between these molecules, and it is known as. It is very similar to the van der Waals potential from before. This is a mean field potential approximation. So, oh, yeah, minus 2 r naught over r to the 6th. And you can think of you can think of how this potential actually looks when you plot it. You basically expect it to sort of go off to infinity as the particles get close to each other, and go up to 0 as the distance increases, which is precisely what this function looks like. So u of r is just goes off to infinity and then reaches a minimum, and then something like that. Yeah. And this is r. And if you actually plot the virial coefficients that we just derived, b of t, with this Leonard-Jones potential for various temperatures, it looks something like this. So this is b of t normalized to r naught cubed, which is the size of your particle cubed, radius cubed, and kbt, the temperature scale, normalized to your potential energy. And this looks something like this for real-world materials. Real-world materials, you know, can be any gas like hydrogen, helium, whatever. Yeah. And you can also you can also plot the virial coefficient as well for various temperatures, and the way it looks is something like this. Something like that. So this is how the virial coefficient appears. So I hope you guys were able to take away something from this. This is how physicists often use statistical mechanics to deal with these complicated interacting systems where particles exert forces on each other, and you can't really do a first principles calculation for thermodynamic quantities very easily, unless you resort to approximations and schemes like this. And modern statistical mechanics is all about devising these sorts of techniques and these mathematical techniques to sort of approximate these thermodynamic quantities. Um, all right, I want to wrap it up there. Thank you.